Welcome to our next Athena Institute seminar. Today we have Ruiyang Zhu, who's a fifth-year PhD student in computer science and engineering at the University of Michigan and advised by Professor Morley Mao. His primary research interests broadly include computer systems and networks, with a focus on mobile networks and network systems. His current research focuses on cooperative perception on connected and autonomous vehicles. His work has been featured in the Athena Institute's Situational Awareness and Collaborative XR demonstration. And he has numerous publications and conference papers. So thank you, Ruiyang. Take it away.
Yeah, thank you, Rajashi. I'm glad that I can present my research at Athena AI Institute seminar talk, and welcome everyone to join both online and in person. My presentation today is titled Enhancing 3D Collaborative Vehicular Perception, Hybrid Communication, and Asynchronous Sensor Fusion. So I'll be excited to share some of our experience in designing like network systems for connected and autonomous vehicles to enhance their perception capability of the environments and making better driving decisions. And this work is supported by my advisor, Professor Morley Mao at the University of Michigan. So just a little bit of a background. So what is collaborative vehicular perception? So you know that currently there are like developments of autonomous vehicles are like a widely hot topic. For example, you know that Waymo has deployed robot taxi, autonomous driving taxis in many cities, including San Francisco and etc. So for autonomous vehicles, they are cyber physical systems integrated with both computation capability of sensing the environments with multiple sensors, including both cameras, lidars, radars, and etc. And many of those sensors, they capture different format of the environment. For example, LiDAR captures 3D point clouds representation of the environment, and the camera captures like RGB and 2D images of the environment. So a common drawbacks or limitations of such in autonomous vehicle system is that often those onboard sensors, they are processed with the perception algorithm to do like object detection or area segmentations of the environment to basically help the vehicle understanding what is the driving environment of it. And the limitation of those sensors is that they are often limited by line of sight, which means that they cannot see through objects. For example, if there are objects near or in behind that the ego vehicles, they will create a lot of blind spots, which may limit the understanding of the ego vehicle of the environment. And this will happen both for the drivable space detection and object detection algorithm as well. So as a emerging technology to mitigate or address these problems is through like a data sharing or through like a wireless network, because currently vehicles, they often equipped with not only the sensing capability, but also with the communication capability. So for example, here's like an illustration of what it looks like if we combine the two sensing data from both the ego vehicle and another vehicle nearby. So you will see that the point clouds or the 3D LiDAR point clouds, they eliminate a few blind spots in the occluded area of the ego vehicle, making that the ego vehicle able to increase its sensing range, and also detecting potential objects that are inside the occluded area to make better driving decisions. So we call this paradigm collaborative vehicular perception, which is essentially a a network system that allow vehicle to exchange their sensor data to extend their sensing capabilities. So yeah, based on this, so what are the actual challenges in designing such CVP systems? And what are we actually care for or optimize for? So there are multiple aspects that are important and make CVP system realistic enough to give like a good perception performance in the real world. So, for example, the three main aspects or challenges we need to deal with is the first of all, we have like heterogeneous sensors and devices. For example, assuming multiple connected vehicles, they have like a different sensor modalities or different sensor capabilities, or even if they have the same sensor, their sensors clock are not well synchronized, and the data capture will, of those sensors will differ in like global timestamps and causing some deviation of the when we try to merge the sensor data together for better perception of the environment. And on the other hand, because we are sharing sensor data through the network, the wireless network is a very unstable medium, which may limit the communication bandwidth and communication delay for sharing the sensor data across vehicles. We don't want our data sharing to consume too much bandwidth or too long communication delay, which will greatly hurt the performance of autonomous driving because it's more like a real-time system that need to make driving decisions promptly. And of course, there are other concerns, including security and privacy, which is less of a focus of the talk today. But if you have any questions regarding this, I'll be happy to discuss with you. So for the first part of this presentation, we will present our research work to design a robust real-time CVP systems on asynchronous sensors. Basically meaning that we are dealing with the heterogeneous sensors and devices across autonomous vehicles while maintaining like a good trade-off to use low communication bandwidth to allow the CVP to perform well under those asynchronous sensors in real time. And on the second part, I will present our some of our designs to further enhance the communication part of the CVP system by using like a hybrid architecture for leveraging both the vehicle-to-vehicle communication and the vehicle-to-infrastructure communication to enhance the performance of the CVP systems. Okay, so yeah, let's begin with the first part of the presentation. So yeah, the title of the first part is the robust real-time multi-vehicle collaboration on asynchronous sensors. So this is our research work that we published on Mobicom 23. And the motivation for this, as I just mentioned, in the context of those multi-vehicle collaboration for collaborative perception, the LiDAR point cloud or LiDAR images to be merged to do the final prediction is not captured on the same timestamp. For example, you can imagine that one vehicle, which we named the producer here, who is basically sharing their sensor data to another vehicles, which we call consumer here. They are equipped with both LiDAR sensors, but their LiDAR sensors, the clock of those two LiDAR sensors are not synchronized because of many real world reasons. You could imagine that even the two same LiDAR sensors, they are not gonna capture the same environment at the exact same time. Yeah, because there are clock deviations and hardware constraints and etc. And also, there are also data processing and data transmission delays. For example, to reduce the network bandwidth from sharing an entire point cloud from one to the other. There are algorithms to basically partition and select which part of data to be transferred from the one vehicle to another. So the data, both the data processing and data transmission, they will cause additional delay from when a LiDAR point cloud is captured to where the LiDAR point cloud is received by the consumer side. So this means that when at the consumer side, it wants to leverage some shared data from the producer side. The shared data may be already stale because of both the asynchronous features of the sensors and also the additional data processing delays caused by any other algorithms. Therefore, the perception is basically the data fusion steps before the perception will cause that the actual captured point cloud to be misaligned with the received point cloud, which is a little bit of the stale data, for example, like a few hundred milliseconds ago. So to give you a sense of what it will looks like in reality, here's a short examples showing a road situation diagram of two vehicles. They are collaborating to share their sensor data together. The E here stands for the ego vehicle, which is basically the consumer, and the A stands for another collaborator vehicles, which stands for the producer. And the blue points is a point cloud that's captured by the ego vehicle, and the red point is the point cloud from the neighbors or the producer. So in the ideal synchronization scenarios, you will imagine that, for example, there are multiple vehicles on the road, and after fusing the data from both the producer and the consumer, we will find that those vehicles are perfectly synchronized, and you can see the ground truth and the predictions, they align pretty well to each other. However, if we consider both the sensor the asynchronous features of sensors and also the transmission delay caused by data processing and network, what in reality the ego vehicles will receive something like the right-hand side one. So you will see that the points from the neighbors are shifted, and if we directly merge them together, you will see that the same vehicle is either like shifted outside, or there are like large misalignment to cause the one vehicle to become two actually. So this is the first motivation for us to design a system that can handle such synchronization across the multiple vehicles. And the second motivation we have is prior work on this field often rely on like a blind spot estimation, basically to determine what data to share between the vehicles. And their approach can be inaccurate because of a few reasons I'm going to talk about shortly. So as I mentioned before, sharing like entire point clouds is not like very efficient because there are a lot of redundant data, and also it requires like very high network bandwidth to do so. So prior work designing like CVP systems employ a strategy basically to try to only share some partial data that are inside the blind spot of the other vehicles, which may be helpful for the consumer side. And the existing systems is the performance of the existing systems are limited because their data sharing strategies have some issues. For example, a prior work AutoCast, they estimate blind spot based on the observed objects through a naive recasting algorithm from the producer side. So this will cause problems which we showed in the diagram here in two cases. First of all, because this data sharing is producer driven, so the producer needs to estimate what are the blind spots of the consumer side and what are data needed by the consumer itself. And if some obstacles are not detected by the producer, for example, example showing on the left image, if the obstacle is not detected by the producer itself, so it cannot actually estimate any blind spot caused by this object to the consumer side. And the second aspect of the inaccurate blind spot estimation is that if the producer can only detect part of the obstacle, for example, on the right-hand side, the vehicle, the producer can only detect one side of the vehicle, and it estimates the consumer blind spots based on its own detection. The estimated blind spot will be smaller than the real blind spot actually perceived by the consumer, making this data sharing less efficient. So based on these two observations of the current limitations, we would like to basically design a system that handle these two types of issues. And two key questions to answer in this part in the system design. So how do we handle the synchronization problems on multiple vehicle LiDAR sensors? The answer is pretty straightforward. So we try to leverage prediction. Basically, we try to design prediction algorithm to synchronize LiDAR point clouds to the same timestamp of where the consumer vehicle is actually using the data. And how do we do accurate blind spot estimation is another issue, which we propose an on-demand data sharing scheme. At high level is that instead of you let the producer to estimate what the consumer needs, we let the consumer vehicles to proactively request the data based on their own observations of the environments, and which can be more accurate and precise. So we'll a little bit more details into our actual like algorithm and system design. So what we do to deal with the prediction part is we let all the CVs or the connected vehicles to share a metadata, a processed metadata called occupancy maps, which is basically a 2D area segmentation of the environment. So what we do firstly is with each LiDAR point clouds or LiDAR images captured at the vehicle side, we do a point segmentation to classify the point to be in the background in the background road or some like obstacles or potential objects. And based on the point segmentations, we perform area segmentations using convex Hall algorithms to classify those potential objects that can create the blind spots. And then we basically remove those areas with we basically remove those free areas with visibilities and calculate the remaining areas that's caused by the obstacles as the blind spot as the blind spot detection. And to do the predictions, we basically leverage our object tracking algorithm basically to match those fine-grained polygons that are classified as potential objects through a series of time. And based on the prediction and our object tracking algorithm, we basically estimate what are the changes of the blind spot area in the near future. And through this motion estimation, so we basically try to predict what are the blind spot areas that are, for example, 100 milliseconds later in time, and when the consumer receive those information, so they will have like a synchronized blind spot area estimation. And in this case, so they will process the data based on the actual predicted blind spot instead of the original observation, which is already stale. And at the consumer side, so they prepare data requests based on the occupancy map algorithm I just mentioned. And for the data sharing, we basically the prediction is always gonna do the the data for the next LiDAR cycle instead of the current LiDAR cycle, which is which can be already still based on the data processing. So assuming we have both the local occupancy map from the consumer side and also the producer occupancy map. So we first do a map prediction to the next LiDAR cycle of what it will look like in the future. And then we basically synchronize those occupancy map to the same timestamp of the next LiDAR cycle where the ego vehicles or the consumer vehicle will produce another LiDAR measurement. And then we use a data occlusion aware data scheduling algorithm to schedule this data transmission and then when the data is arrived, so it's already synchronized to the next cycle, which can be immediately used by the downstream perception algorithms. So on the producer side, so they are responsible to share the request data from the consumer side, which is already synchronized to a future timestamp based on the predictions. And whenever a producer receive a point cloud sharing request, data sharing request, so they will process their latest point cloud on the requested areas made by the consumers and try to synchronize the point cloud to the request timestamps made by the consumer themselves. So in this case, even though the consumer vehicles is making the stale request, so it's requesting some basically a little bit of a future information for it to use, and the producer can, based on this, to also do some predictions based on its own observation of the area, and then crop those point cloud data and send it back to the consumer for it to enhance their perception capability. So that's the basically the key algorithm and the pipeline of the system. Yeah, to integrate everything I just mentioned into end-to-end pipeline, so we basically implement and execute all the data processing pipeline in parallel to avoid any more of a data processing delay. So in this case, the producer and the consumer side, they are running in an event-based system, and each of their processes, except for the dependency ones, the process, they do not block each other and will run concurrently to avoid any additional data processing delay in addition to the final perception. So in this case, for example, the producer is running the occupancy map with the motion prediction algorithm, and they partition the synchronized LiDAR image and share it through the V2V network. And on the same time, the consumer side will also do the point clustering and occupancy map prediction to make the next data scheduling and then the next request for its future point clouds for fusion and detection. So in this case, the only delay compared to a single vehicle perception system is for the data fusion. So you can imagine that when a consumer they capture a new LiDAR image, so they will use basically they will use whatever is the latest shared data, and that data is already predicted and synchronized to its to the timestamp of this newly captured LiDAR image, and they can just fuse the LiDAR image with the received shared data from the other vehicles to do the data fusion and then do the perception. So we evaluate our system named RAW on two different data sets, including both simulated one and the real world ones, and we compare the perception accuracy under the existence of asynchronous sensor data with two prior work, EMP and AutoCast. Yeah, for the perceptions we use existing perception deep learning perception model point pillars as the base perception ones, and compare like the perception accuracy at the IOU of 0.5 and 0.7 on these two different data sets. So for the results, we observe that our systems, which is asynchronous data sensor data aware, achieves like a better perception accuracy compared to the baseline method, and also greatly enhance the perception capability compared to local only perception, which does not use any collaboration data from the nearby vehicles. Yeah, we also provide a small benchmark study at one of the real world purpose-built autonomous vehicle testbed called MCD here at Michigan, and we also find similar results by basically by incorporating the designs into asynchronous sensors, and also like more accurate blind spot estimation. Our system is gonna enhance the perception capability for autonomous vehicles compared to existing collaborative perception baselines and also the local only perception. Yeah, so for the overhead of our systems, we also do some measurements and calculations of both the data sharing needs and also the latency requirements. So the total average latency of all the modules I mentioned previously is around like 80 milliseconds, which allow us to process the LiDAR point cloud at a regular 4 frame rate at 10 frame per second, which is also the standard frame rate used by many of the LiDAR sensors, which basically indicates that our system can suit the real-time needs for the vehicles to run a cooperative perception algorithm that is aware of the sensor asynchrony and also the accurate blind spot estimation. And compared to prior work, we observe that we have like a similar data overhead compared to the state of the art. For example, both EMP and AutoCAD, they have some algorithm to partition and cut the point cloud to reduce the bandwidth needed for sharing. And same for us, because we only share the blind spot area. So we can further reduce the number of LiDAR points shared by the vehicles for each frame. And the only additional data we incur is the occupancy map, which is more like a 2D representation of the environment. But at data side, it's only like 1.7 kilobytes of data, which is not very much compared to the actual sensing data of LiDAR point cloud sharing. And yeah, in conclusion, so our system incurs like a similar data overhead that is not very high for vehicular communication, and also we can achieve like a real-time execution needs for the connected autonomous vehicles to perform collaborative perception in real time with this real-world constraints. Yeah, at the end of the first part, I will show you a case study that we did at the MCD testbed here. The scenario is on the left bottom hand side of the slide. So basically, we designed like an unprotected right turn scenario where the Eagle vehicle is trying to turn right at one intersection, and there's a non-connected vehicle is blocking the Eagle's CV's view on its left hand side, and there's actually a target vehicle that tries to go straight in the same time at these intersections, which is not actually visible by the Eagle CV. And there's another vehicle, connected vehicles on around the corner that can actually visualize this target vehicle. Through cooperation, you will see that for example, without any accurate blind spot estimation like the prior work EMP, you will see that only part of the vehicles is visible to the Eagle vehicle, and without a very accurate synchronous aware algorithm to fuse the data, you will see that the AutoCAD systems, they actually break the one vehicles to like a sort of a two-part, where the red part only have the front side of vehicles and the blue part only have the back side of the vehicles. And in our system, by combining these two mechanisms, you will see that the observation from the ego vehicle side is now more complete, because we have more accurate estimation of um, the time difference between the sensors, and also we have more accurate localization of the blind spot areas from the ego vehicles, which makes this detection of this target vehicle easier. And yeah, on the right bottom hand side, you will see that the trajectories of the target vehicles observed by the ego vehicles is completely visible through the entire running period of these scenarios, while there are a few missing points that are meaning that these target vehicles are not detected by other existing collaborative perception methods. Yeah, so that to this end, this is the last part of the first part of the presentation, and yeah. So next, I will go into the second part, which is boosting collaborative vehicular perception on the edge with vehicle-to-vehicle communication. So in this part, I'll present another basically research work from our group that tries to further enhance the CVP systems with better communication capability and a more stable communication performance in terms of the end-to-end detection. Yeah, and this work is published at Census 24 as a conference paper. Yeah. In addition to the synchronization problems and estimation of blind spots, the existing designs of the CVP systems, they often leverage one of the two communication paradigm. The first communication paradigm is called V2V CVP systems. It's more like so for the network used in the underlying systems, it's more like a peer-to-peer data sharing paradigm. For example, vehicle to vehicles, they connected with a local Wi-Fi network, and they the cars, autonomous vehicles, they have their sensor data frames, and they somehow compress or partition those sensor data frames using some compression algorithm, and they send this data through the Wi-Fi network or peer-to-peer network to the ego vehicles, and the ego vehicle is performing a data merging to aggregate the other vehicle's data with its own, and then do the detection or perception for the environments, and then maybe depending on the design, they can disseminate these sensing results to other vehicles, or each vehicles they can do their own detection at the same time. So yeah, so we call this type of design a vehicle-to-vehicle CVP systems, and this is often adopted by earlier works in the field because this paradigm is pretty simple, and some of the existing work they further simplify this by assuming there's only two vehicles that are collaborating with each other, which means that the data sharing part of the in the network is only like a one-to-one communication. And another type of designs is using a edge cloud or a cloud server to aggregate data from multiple vehicles. We call this central server-based data sharing. So similarly, multiple vehicles that they want to do the collaborative perception together, they will do the data compression and upload their data to some cloud or edge server for data merging and also the detection. And after these detections, the edge server can disseminate or send back the sensing results by basically aggregating multiple vehicles data together to have like a better coverage of the environment and better perception of the environment. So the default communication method used in this type of system is so-called vehicle to infrastructure or vehicle to edge, or V2I for short. And yeah, as I mentioned, so it requires a central server that can aggregate data to perform computation. So this type of systems, they have an advantage over the V2V based systems, meaning that if the number of vehicles increases, each vehicle only send one copy of its data to one central entity instead of broadcasting its data to every peer nearby. So that's it can be more scalable in terms of sharing the number of copies of data and yeah, reducing the actual bandwidth requirements for the vehicles to collaborate with each other. Yeah, if there are more than two vehicles. And both of these two mechanisms, they have some limitations or drawbacks. For example, as I mentioned previously, for V2V only CVP, so they can be lack of scalability for larger number of vehicles. For example, in the two vehicle case, it's pretty standard easy. So there are one-to-one communication from one vehicle to another. If there are more than three vehicles, either the system needs to decide whether to broadcast the data over the wireless network, or it needs to establish like a one-to-one communication for each pair of the vehicle in the system, which is which means that there's like an n-squared bandwidth sharing requirements if the vehicles want to share all this data from all its peers. So all these two different type of designs, they will not be very scalable because the broadcast will largely hurt the wireless medium with limited bandwidth. And the one-to-one communication for all pairs will greatly increase the complexity and also the bandwidth requirements in the wireless network. And for the V2I only CVP, there are also several issues. For example, a widely used cellular network for vehicle to cloud or vehicle to edge communication, the performance can vary temporally and spatially by a lot. For example, here's a measurement case that we found by driving the car in the urban road using two different cellular providers. We will see that while there are some different carriers, they have very different performance and coverage on different roads, meaning that at some places using Verizon, for example, you have very good uplink performance to basically upload your sensor data to the cloud, while at some other locations, using another carrier can have a much better performance compared to using the Verizon at this place. So this will hurt the performance of V2I only CVP system, because now if some vehicles is using this carrier at this road, they are having very poor performance, network performance to upload their data, while there are potentially other vehicles using some other carriers, they have very good network performance at this place, and their bandwidth remains underutilized to basically aggregate the data from different agents, and thus their performance are basically the data are not their sensing data cannot be delivered timely to the cloud, so that the collaboration basically fall apart. So based on these two observations, so we further have a design for a hybrid architecture to solve these problems. So yeah, the key idea of our proposed system, Harbor, a hybrid architecture for collaborative vehicular perception, is to adaptively use both the V2V and the V2I communication technology, and try to bridge those V2I disconnected vehicles, or what we call helpers here, by strategically pairing them with some V2I connected vehicles that have good V2I performance, which we call helper hears, through a V2V communication. So to give you a like high level idea or examples, so assuming these three vehicles, they are trying to use like a V2I based paradigm to do the collaboration, and the red vehicles using ISPB is experience very poor V2I communication at this time. So the system can do a mode switch, which means that the red vehicles can actually use some other vehicles like the black vehicles in the diagram as a relay to help upload this data to the central cloud, so that the cloud can have like a better coverage and of the data from multiple sources to do more accurate perception based on the sensing data of these three vehicles together. So yeah, for our systems, so the design of our system basically composed of basic three elements. We are building our system based on this edge cloud based cooperative perception paradigm, and we classify the vehicles into two categories. One is called helper vehicles, which means at a particular time they have a relative good communication bandwidth with the edge cloud, and another set of vehicles, we call it helpy vehicles, which means that they do not have like a very good communication capability to the edge cloud at a certain timestamp. So the high level idea is that we leverage both the V2V and the V2I network access, and the system is a centralized system that flexibly manage the V2V and the V2I connections by pairing the helpy vehicles to the helper vehicles through a V2V through the V2V network. So basically, for each helpy vehicles, the system designs how to relay the data through a helper vehicles, so that those data can be like a timely delivered to the edge cloud through like a V2V link and a V2I link together. Yeah, so basically we have in the system, we have like three key design components. So one is the strategic helper assignment, which optimize like the network uploading like objective for the point cloud or the sensor data from the both helper and helpy vehicles. And from the application side, we have like a deadline aware view merging and also the MAC layer prioritization to deliver the detection results more promptly. Yeah. So yeah, given the limited time, I will just go through a few high level idea of our designs. So for the help assignments, the optimization's goal is that we want to efficiently assign those helper vehicles to helpy vehicles to speed up their sensor data upload. But there are challenges that different helpers, they have different like V2I and V2V conditions, and also the end-to-end upload performance of the data depends on the network performance on both the V2V pass and the V2I pass. Our key idea is here is to use some identify the performance impacting factors, and we model the system using a basically we propose a model to optimize this data uploading process, and the performance impacting factors included here is direct measures, which is basically just the V2I bandwidth or V2E bandwidth, and some indirect measures that a few factors that can affect those bandwidths. For example, the distance between a helper and helpy vehicles, and whether there are interference caused by like multiple sources of data transmission together at the V2V wireless medium. Yeah, so as we know that both the V2V and P2I paths, the performance can matter because now the data uploading from the helpy vehicles to the clouds need to go through both the a vehicle to vehicle path and a vehicle to infrastructure path. And because the vehicle infrastructure path is more directly measurable, because each vehicle is basically doing heartbeat messages and our data uploading to the central server, so we can directly use the V2I bandwidth as a measure. However, the V2V bandwidth is more hard to quantify if you consider that multiple vehicles, they establish like a Wi-Fi network. So it's very hard to do probings between every pair of the vehicles because this will cause a very large overhead and can be inaccurate. So in this case, we will use like indirect measures and some heuristics to basically model the V2V bandwidth. And yeah, so I won't go through too many of the details here due to the time, but if you're interested, you can look at our papers. So at high level, we propose like a heuristic a utility function that try to maximize a pairing score for each pair of the helpy vehicle and the helper vehicles. And this utility function is run periodically to adapt to vehicle mobility and the network state changes. Yeah, in addition to the strategy and in addition to the helper assignment, we also do some system level optimizations to make the overall pipeline like more efficient. For example, because at the server side, it needs to receive like multiple vehicles data together to do the data fusion and the detection. It's sorry, it's vital to deliver the remote detection results back to the vehicle in time. So in this case, we design like application layer deadline to force the server to make prompt fusion and detection based on a vehicle side deadline. So which means that whenever the server deadline is met, no matter how many data it receives from vehicles, it needs to do at least a detection. Otherwise, it will otherwise the vehicle side deadline may be missed, and the detection results can be stale. Yeah, and then the one last part of the design is that because these sensing results are delivered back to both the helper and helpy vehicles, from the helper to helpy path, is the data needs to go through a V2V wireless network, which is like more like a shared medium. And in the same time, the helpy vehicles is sending their like bandwidth intensive sensor data stream to the helper vehicles. And these two sides of data transmission, they will cause a contention to the same wireless medium and will cause delays in the final detection result delivery. So to optimize this, our key idea is to prioritize those small but latency sensitive traffic over the bulk data transfer, which is also a very standard approach in the network system design. And a little bit more details on how we achieve that is that we modified the 802.11 MAC transmission queue under the system kernel, and in order to let those small but time critical information to be delivered with a higher priority compared to the bandwidth intensive data stream. So we give them higher priority in the transmission queues for the detection results compared to the sensor data streams. So in this case, detection results is gonna have like higher chance to get a medium, and so that the results are delivered to the helpy vehicles faster. But at the same time, those detection result messages are very small, so they will consume like a very less of the bandwidth. So the sensor data streams remains like unaffected. Yeah. So yeah, a few of the evaluation results similarly to previous ones. So we compare with the existing collaborative perception methods that are built on top of only V2V communication or only V2I communication. And we find that our system proposes a system hardware that outperforms all the V2V and the V2I sharing schemes in terms of detection latency and the detection accuracy in the average case. Yeah, in addition to some emulation type of experiments using simulation data set from the simulator, we also perform some real world driving experiments by driving 3 to 6 vehicles around our university campuses and replace the sensor data using using real world like a vehicle to vehicle Wi-Fi network and also vehicle to infrastructure cellular network to test the performance of our systems. And similarly, we observe like a higher performance in terms of both accuracy and latency compared to the existing methods. Yeah, finally, we have some like end-to-end evaluation at the MCT testbed using by employing our system and some of the baseline system into the planning into the planning module of the Baidu Apollo software for autonomous driving. And we show that by employing harbor with both V2V and V2I communication results in the testbed of the 4 driving cases, we are having like a better driving outcome by increasing both the driving reaction time for the ego vehicle to make prompt and correct driving decisions and reduce crash scenarios, reduce the crash scenarios of several cases in the test bed, and of course in terms of perception accuracy, we also outperforms the existing methods. Yeah. Again, another like quick case study of the perception benefits brought by this hybrid V2V plus V2I architecture. Similarly, it's still the same example from the first part, like the right turn unprotected right turn example. In this case, the CV is also turning right, where the target vehicle is not visible, directly visible to the ego vehicle. And our baseline methods, they suffer from 2 reasons. For the V2I based only, for the V2I only baselines, they have one of the collaborator, they have they do not have like good V2I connections, so they will not share the data at this time. And for the V2V only baselines, one of the vehicles have low V2V bandwidth to the ego vehicles. So on the left part of the diagram, so the data is missing. While based on our designs, both these 2 vehicles can successfully upload their data to the edge cloud and be merged and detected together, because that's the CVB is now be able to share their data upload through the helper vehicle A to the edge, and the helper vehicle A, they have like a better V2I bandwidth. So in this case, all the 3 vehicles data can be timely aggregated, and also the perception performance is becoming better than the baseline method and also the local only perception. Yeah, so with that, I'd like to conclude the presentation for this seminar talk, and I'd be happy to take any questions.
Thank you, Ruiyang. You can also write your questions in the chat. No questions. Thank you so much for attending.
Yeah, thanks everyone.
Bye-bye.